And we're back. Welcome back and happy Tuesday. Today, we will continue in our discussion of image representation, looking at so-called appearance-based type features that go above and beyond just the edge maps. But before we begin, some administrative bits. Homework number 2 will be due this Thursday, the 25th of February, at the usual 11:59 and 59 seconds p.m., 1 second before the stroke of midnight. So why don't we begin? When we last left off, we talked about the intensity surface in a more robust way of depicting a line. We took the central difference operator and we cleaned up the mask values by multiplying by 2, and we did that for all of our edge points, 3 in a row, because 3 edge points in a row that have a large gradient is more robust than just a single edge point. So we repeated our convolution mask 3 times, 1 for the top edge point, 1 for the middle edge point, and 1 for the bottom edge point. And so we did this, and we generalized it to take the partial derivative with respect to x. So we compute that mask from left to right, and the computation of the partial derivative with respect to y. We compute that mask from top to bottom. And in doing so, we can also take our gradient or derivatives with respect to x with respect to y and compute the edge magnitude using the Pythagorean theorem and compute m, the edge magnitude. And we can also take the inverse tangent of the edge component in the y direction over the edge component in the x direction, and the inverse tangent of that gives you the edge orientation angle theta. And so we talked a little bit about the Pruitt operator and the Sobel operator, where the difference is the emphasis placed by the Sobel operator on the center edge pixel. Okay, so let's take a look at additional representation for appearance. And more generally, appearance-based features represent the color of the objects depicted in the image, as well as the shape for the objects depicted in the image. Let's take a look at this image of a building. Now, if we were to look at the color, well, we see some greens for the grass and the shrubbery. We see the blue for the sky with a little bit of white for the clouds. And then the building itself is mostly gray, different shades of gray. If we look at the shape or the edges for the building, well, we see a lot of edges that are up and down, that are 90 degrees, and a lot of edges that are left and right, that are 180 degrees. And so human-engineered objects, buildings and houses, they tend to have a lot of straight edges. And if we were to look at the distribution of the edge orientations, those angles theta, we're going to see some peaks in that histogram corresponding to 90 degrees, because there are a lot of vertical edges, and 180 degrees because there are a lot of horizontal edges. And moreover, for the color representation, we're going to see high peaks in the histogram corresponding to those components in the red, green, blue color channels that represent the blue for the sky, that represent the green for the grass. If we look at this image on the right-hand side, we see a field of sunflowers. Now, sunflowers are round, and round things tend to be uniform in their edge orientation. So we have roughly equal representation, as it were, for edges, edge angles, theta. Because of all these round things, we have the roundness of the outside of the sunflower, we have the roundness of the inside, we have another circle right here. Moreover, if you look at the petals, it's round. It comes to a point, yes, but it has edges at lots of different orientations. And so in the edge map, for the edge orientation, theta, we're going to see something closer to a uniform distribution corresponding to the shape or the edges that comprise this sunflower image. And that's in contrast to this bimodal distribution with a peak over 180 and a peak over 90 corresponding to these edges that you might see associated with the building. If we look at the colors in the sunflower field, well, we have yellows. So we're going to have a high peak in the color histogram corresponding to the contribution for the yellow color for the sunflower, as well as the green for the leaves, but it's a different green from the green here in the building. And then for the sky in this sunflower image, we're going to have a lot more clouds, but we're going to also have blue. So that blue is going to be lighter in the intensity for the red, green, and blue channel representing color for the sunflowers. And so here, when we talk about appearance-based features, we want to represent somehow both the color, distribution of the colors, as well as the shape, the distribution over the edges that are in the image. And so the color is the distribution of red, green, and blue, and the shape is the distribution of edges, both their magnitude and or their angle. All right. So let's take this idea of the distribution of colors. So we have our picture of the building on the left, and we have our picture of the sunflower field on the right. So let's extract the red, green, and blue channels. So there's our red channel, there's our green channel, and there's our blue channel for the building. And we compute the intensity for the red channel, the green channel, blue channel, likewise for the sunflower field. So now then, suppose we depicted this red channel as 10 bins for the histogram for red, 10 bins for the histogram for green, 10 bins for the histogram for blue. We do the same with the sunflower field. So that's 10 bins for red, green, and blue color channels for the intensities in red, intensities in green, and the intensities in blue. So then we collect these bin counts and we concatenate them to form a single vector. Because we have a contribution of 10 bin counts from red, green, and blue color channels for these 10 histograms, respectively, for each one of the color channels, we put them together and we form a single 30 vector. And so this 30 vector from the building would represent the color content of the entire image of the building. And likewise, the 30 vector for the sunflower field is going to represent the color content for that sunflower field. Now, because the colors are different in these images, these 30 vectors are also going to be different. Okay, so let's do the same with the edge map for edge orientation. We take our image for the building, we compute the edge map with respect to x and with respect to y. We compute theta through the inverse tangent of the y derivative over the x derivative, and then we take that edge map containing edge angles and we compute a histogram consisting of 10 bins. And so this particular histogram, as we said before, would have two peaks, one peak over 180 degrees and another peak over 90 degrees, representing the dominant edge orientations in this particular image. The edge map for the sunflower field will be closer to a uniform distribution because we have representation from very many different edge orientations from 0 to 360. And so likewise, we compute the derivative with respect to x, the derivative with respect to y for the sunflower image, and then we take the edge map representing the edges, and then we compute 10 bins. Now, of course, if you're doing the edge map, color is not important, so you'd first convert to RGB for the building image and RGB for the sunflower image. Okay, so now you have these 10 bins, and you take those bin counts representing the edge features or the shape description for the content of the edges of the image, and then you do also the same for the sunflower image, its histogram of edge orientations theta. Those 10 bins, those bin counts, represent the shape content for this image of the sunflower field. So now then, you take your color and your shape. So we had our 30 vector representing the color. We had our 10 vector representing the shape, and we put them together to form a single 40 vector. We do the same thing for our sunflower field picture. We take the 30 vector for the color, that's red, green, and blue, 10 histograms each, and then another 10 histograms for the edge orientation histogram, and that is our 40 vector representing the appearance, the color and shape for our sunflower field picture. So we put them together to form an image representation, and this is going to be the representation of the content for each of these images. Now, let's describe this mathematically as a vector. This vector, each one of these images, a unique image, corresponds to a unique set of 40 vectors, one for each image, both the color and the shape component. And so we can describe this mathematically as a 40 vector. We have the ith vector corresponding to the ith image in some number of images or image database. And we have the first component, which is the first feature, the second component, which is the second feature, xi2, up to and including xi40, which is the 40th feature. Now, of course, the first 30 features represent the colors, which is the first 10 descriptors of the red, the next 10 for the green, and the next 10 for the blue, and then that last 10, that's for the shape, the edge orientation histogram. So this is how we'd represent it mathematically. Each of these 40 vectors is some point in some d-dimensional feature space representation. And so this is the first ith vector, the first feature, second feature, and so we'd have feature number xi1 through xi10. That's going to be the red, so that's our red. We're going to have xi11 through xi20. That's going to be the green, and then we're going to have xi21 through xi30. That's going to be the blue, and then lastly xi31 ... through xi40. That's going to be theta, our edge descriptors. Okay, and so each one of these positions in the vector represents a feature, and that feature is computed from the bin counts of the respective histograms for color, each color channel, and shape, the edge orientation, theta. All right, and so each image then is represented as vector in 40 dimensions, and we like to think of this as a point in 40-dimensional feature space. The same way you can have a point in 2-dimensional feature space. We call that the first coordinate, and we call that projection the second coordinate. All right, so let's assume, for the sake of consideration, instead of going to 40 dimensions, we were going to 2 dimensions. And as such, let's say this building image is our first image, x1, and this sunflower field picture is our second image. We'll just call that x2. And so the features x11 and x12 is the first feature for the building image and the second feature for the building image. And then x21 and x22, that's the first feature for the sunflower image. And we have the second feature for the sunflower image. Now, of course, we can represent images, in this case, is 2D vectors. And we're using 2D because it's easy to demonstrate on a PowerPoint slide. And so here we have x1. And we have point x2, and this is our sunflower image. Now, x11 is just that projection, or that first feature, projection of that first point in 2 dimensions along the horizontal axis, and then x12, the second feature, is treated as a projection of that point along the second axis, the vertical axis. Likewise, we can do the same with the sunflower image. It has a value for the first feature, x21, and it also has a value for the second feature that we're calling x22. All right, and so this is how we think of points, and now we can treat these images as points in 2 dimensions because we're representing each one of these images' content as a 2 vector, right? So we have 2 positions, 2 measurements, if you will. And so you can also treat these images, if they're points in 2 dimensions, you can also draw a line between origin and each point and treat them then as vectors in 2 dimensions. And so why do we do this? Well, because if you want to compare the content in images, now you have available to you the tools of vector algebra. And so as vectors, we project onto each feature axis in order to find the feature values that collectively describe the content of each one of these images, which is represented as a point in as many dimensions as we have features. And so we have 2 features here, and therefore we have 2 dimensions. And so first thing we might want an enterprise to do is assess, well, how different are these images? All right, so if you want to draw that comparison, now this is where these tools from vector algebra come into play. The question of how different these images are based on this appearance-based description, i.e. of their content, now we want to just take the distance between them. Because if they are very similar to one another, they're going to be close together in their feature values, and the points will be distance-wise nearby. If they are very different from one another, their feature values are going to be different, and mathematically they will be distance-wise far apart from one another. So what we enterprise to do when we ask the question mathematically, how different are these images? And this is something that we can mechanize. We can write a program to do this. The question we're really asking is, what is the distance between these points representing these images in two-dimensional feature space representation in this example? And so there are lots of things we can do. We can use the Euclidean distance. So we just take the difference between the vectors for each component, whether it's the x1 axis, x2 axis, and we can generalize that to d dimensions. But we take the component-wise difference or feature-wise difference between these 2 points or these 2 vectors. We square that difference, sum the squares, and take the square root of that result. And that is the so-called Euclidean distance, or the L2 norm. And so we can also treating them as vectors, we can also measure that difference between the 2 images expressed as vectors as the angle between those vectors. And so going back to the definition of the dot product, we have the first vector A dot the second vector B is just the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. And so doing a little bit of algebra, we divide both sides of equality by magnitude A, magnitude B, and we get the cosine of the angle between the 2 vectors A and B is equal to A dot B, the dot product between the 2, divided by magnitude A times magnitude B. Okay, and so this has a name. This quantity is called the cosine distance. So this cosine distance is another way of measuring how similar in content are the two images, or is this building image from the sunflower field image. So let's try this out in Matlab. And we're going to demonstrate this with 4 pictures. And these pictures, 2 of them are similar to one another, to 2 groups of 2. And we'll actually show how this cosine distance works in practice, and also think about some of the practical trade-offs associated with representations. So with that, I will meet you in Matlab. Okay, we're here in Matlab, and we have 4 images, apple 1, apple 2, and these are both pictures of apples. And we have dog 1 and dog 2, and those are pictures of 2 different dogs, but they're the same breed. We set in line 6 through 8 some convenience scalars, constants, and this is so that we can pick out the red plane, the green plane, the blue plane from our RGB color space representation. And we start out, let's start with the number of bins for our histogram is 10 bins. Okay, so we have image rows and columns, and the images are different sizes, and so we're going to resize each one of our images, these 4, to the same size, because if you don't have the same size, you have a larger pixel count, and it throws off the results for the histograms. And so here we have 620 by 480, so that's VGA resolution. We take our images, we read them in, and we resize them to be 620 rows, so that's the Y direction, and 480 columns, that's the X direction. And so we resize all of our images. IA1 is the image for apple 1, IA2 is the image for apple 2, ID1 is the image for dog 1, ID2 is the image for dog 2. So then after that, we give them some titles and we plot them all. Okay, so now that we do that, we're going to take a measurement of the image, and now we're going to create a data structure that's just going to be each slice of the RGB color space representation for each image. So we have rows by columns, 620 by 480, rows and columns, so that's the number of pixels for the red plane, the green plane, and the blue plane. And so we're just going to treat this as an intensity. So you notice here when I allocate an M by N array, rows by columns, I say uint8 for unsigned 8-bit integer, because I'm just storing the intensities for the red color channel, the intensities for the green color channel, and the intensities for the blue. It's unsigned 8-bit integer because the values for intensity go from 0 to 255. And so you need 8 bits unsigned in order to represent that. So now we populate those data structures by pulling out, here we have don't care for the rows and the columns, but then pay attention to the red, which was 1, the first slice, green, the second slice, and blue the third slice in that m by n by 3 block that represented the color image. So we pull apart the red, green, and blue color channels, and we do that for the IA1, the apple image number 1, the image of apple 2. We do that for the image of dog 1, and we do that for the image of dog 2. So now that we have all of the color channels separated, now we're going to compute the histogram for each one. And so we compute the histogram using 10 many bins for the red channel, green channel, and blue channel for each one of these images: image for apple 1, image for apple 2, image for dog 1, and image for dog 2. After we compute each histogram, we extract the red values, and these values from the histogram are the bin counts, and we're using the bin counts as our features. And so we have 10 features of red, 10 features of green, 10 features of blue, which are the bin counts for the respective histograms over the color channels for red, green, and blue components of these color images. And so you didn't have to do it this way. You could have used hist counts, and that would just have given you the counts without trying to display the histogram itself. And so that's certainly something you could change, and I direct you to the Matlab documentation to look that all up. And so we do this extraction, and then after we get the counts for red, green, and blue, we concatenate them. And so this is where we form the 30 vector we talked about. So we say, okay, well, we have 10 columns of red, 10 columns of green, 10 columns of blue for the counts. We put them all together into a big vector, the IA1, image for apple 1, vac. So we do all of this for IA1. We do this for apple image 2. We do that for dog image 1. And we do that similar thing for dog image 2. All right, so now that we have them, I compute what I call a design matrix, the statisticians call it. We're going to construct a row matrix, and so this matrix is going to have 4 rows. The first row is going to be the vector, the 30 vector, for the color content of apple image 1. The second row is going to be the color content, red, green, and blue, 10 bins each, for the apple image 2. And then we do so similarly for dog image 1. That's the third row. And then the last row, fourth row, is going to be dog image 2. It's 30 vector, representing 10 bin count, 10 bins of red, 10 bins of green, 10 bins worth of blue for the histogram counts. And so now we take each one of our pairings and we give them some names. And then we go through and take all pairs and we compute the cosine distance. And so here, the dot product part, remember, the cosine distance is A dot B divided by magnitude A times magnitude B. So here, the dot product is just the B vector transpose times A vector. Okay, that's just your inner product or your dot product. And then the magnitude is just the norm, right? The 2 norm. So we say norm A vec 2, norm B vec 2. That's our magnitude. Okay. And so now that we do that, we take the cosine distance, that's the dot product, over the product of the magnitudes, dot part and mag part. We optionally compute the Euclidean distance, but I don't use that. I want to demonstrate the cosine distance here. But I left it in the code for you to tinker around with it. Please do tinker around with it. All right, so now we compute a message actually displaying what the cosine distance is, and then we end. So why don't we go ahead and let's run all of this. So there's a breakpoint here. Let me clear the breakpoint. And let's bring up the figure. And if we look at figure 1, we see a visualization of just what the images look like. And again, these are resized to 620 by 480. And so here's apple 1. Here's apple 2. It's not the same apple, the same or similar type of apple, but not the same apple. Here's dog 1. It's a puppy chocolate lab. Here's dog 2. It's an adult chocolate lab. And so now, if I direct your attention to the command window, you can see the cosine distance, which ranges between 0 and 1. Cosine distance between apple 1 and itself is 1. Between apple 1 and apple 2 is 0.85. They're very similar. Between apple 1 and dog 1 is 0.5 and change, so they're not very similar. Between apple 1 and dog 2 is 0.34. Between apple 1 and apple 2 is 0.85. Between apple 2 and dog 1 is 0.89. Ooh. So it says that apple 2 looks a lot like dog 1. But of course, if you pull up the image, apple 2 and dog 1 don't look a lot like each other. And so one of the things we will try is we're going to change the bin count, because as your bin count increases, the vector gets bigger, and what it's doing is that it's finding a more fine-grained representation of color. So slight variations of red and slight variations of brown are going to be picked up. And so what we're going to do is we're going to adjust the bin count from 10 bins down to 5 bins, because we don't care about very minute differences in red and green and blue. We care about things that are red and things that are not red, things that are brown and things that are not brown. So let's run this again, and let me pull down this histogram. Again, that's a display of what the images look like, and let's look at our second set of results. So when we look at our second set of results, okay, apple 1, cosine distance is 1, okay. Cosine distance of apple 1 and apple 2 is, let's see, it's 0.67. For apple 1, dog 1, 0.18. They're not very similar. Apple 1 and dog 2, 0.17. Apple 2 and apple 1 is 0.67. They're not as similar, but they're closer than to one another than the others. Apple 2 and apple 2 is 1. Apple 2 and dog 1, let's look at that, 0.34. Apple 2 and dog 2 is 0.32. And so this is a lot more precise between what we see and what it calculates or computes. And so one of the considerations when you are designing your appearance-based features, and this is both for the edge orientations, angles theta, those histograms, as well as the histograms for the color content, red, green, and blue, it's going to be really, really important to decide how specific, how fine-grained, or how coarse-grained, i.e. a larger number of bins, that's fine-grained, a smaller number of bins, that's coarse-grained, what the level of specificity is appropriate for your representation. Because here we found when we went from 10 bins down to 5 bins, that 5 bins is a far better way of representing the differences between these particular images. And what we care about is how brown is it or not brown, how red is it or not red, and not what are the variations of red. Okay? All right. So with that, let's go back to PowerPoint. I will meet you in PowerPoint. So we're back in PowerPoint, and just showed a demonstration of using cosine distance as a measurement of similarity based on the appearance, the color component of appearance for different images, the dog and the apples. So we've done this in Matlab, and in the future, we'll have an assignment where you'll use this and make the trade-offs for yourself about the level of specificity needed for good discrimination or distinguishing between images of one type versus another. And you make this choice separately for the color component versus the shape component, because the color and the shape and the shape content within the image is different and has different utility. All right. So with that, that's all I had for today, and we will pick back up next time on Thursday. As usual, please stay healthy, please stay safe, and I'll see you all on Thursday.